In this video, we're going to look at the effects of vertical stretching and shrinking of a graph. Now, well, first let's draw graphically what it means to stretch something vertically or shrink it. So let's say that's my function f of x. To shrink it or to stretch it vertically means that I still have the same starting and ending point and the same behavior, but the behavior is just amplified. And shrinking means it has the same characteristic behavior, but it is damped. Okay. So this one is just like the shifting of vertical and horizontal is sort of easy to visualize, because what we're doing here is we are either increasing the output or we are decreasing the output. Okay. So for example, the transformation is basically taking f of x to c times f of x, some number. And if the c is less than 1, then that's called shrinking. But if c is more than 1, then that is stretching, because then we are increasing the output by some factor. So let's take our standard x squared example. From there I can obtain a graph for 3x squared and I can obtain a graph for 1/3 x squared. So what do those graphs look like? Means if that is x squared, then 3x squared would be stretching that graph vertically. So if I stretch this vertically, right? If I stretch this vertically, it's going to be steeper. But if I shrink it, which is making it 1/3, it's going to be less steep. So that would be 1/3 x squared, whereas this would be 3x squared. Okay, so it's basically we are increasing it by a certain factor. Let's look at an example where let's combine some of the things that we've done so far. Let's say you need to sketch the graph of 1 minus 2x minus 3 squared. So now we are combining a bunch of transformations here. So I would like you to pause the video and try and figure out the step 1 and step 2. Okay. All right, hopefully you figured this one out. So step 1 is identify the base function. The base function here is x squared. That's the simplest function we are dealing with here. Step 2 is to write step by step how we go from x squared to this. So it looks like I start with x squared, then I become x minus 3 squared, then I become 2 times x minus 3 squared, then I become negative 2 times x minus 3 squared, and last become negative 2x minus 3 squared plus 1. Okay, that's one of the ways in which you can get from x squared to the function you're interested in. Now let's label out the transformations. The first one is x to x minus 3. So that is move right by 3. The second one is you multiply f of x by 2 times f of x. So you stretch vertically by a factor of 2. The next one is you're taking f and you're making the output negative, which means you are reflecting on the x-axis. So whatever's positive becomes negative, whatever's negative becomes positive. And lastly, you're taking f of x and you're adding 1 to the output, which means you're moving it up by 1. Okay, now that you have step 1 and 2, step 3 just asks you to draw the graphs. Right? So I'm going to draw them all, let's say, in one plot. So we start with x squared. We move this to the right by 3. So this is 3 comma 0. And we get x minus 3 squared. Then we multiply it by 2 and we make it stretch, but this point doesn't change. It just becomes steeper. So this is 2 times x minus 3 squared. Then we reflect it on the x-axis. So as the reflection of the blue curve, again, the point 3 comma 0 doesn't change. And lastly, we add 1. I'm out of colors. Let's go back to okay, I haven't used. Oh, that's not how that works. Let's use purple. So moving that 1 up, now that would change the 3 comma 0 to 3 comma 1 and parallel to the red. So that would be negative 2 x minus 3 squared plus 1. Okay, so we break this down into a bunch of smaller steps, which we have already seen what they look like in terms of the graphical transformations. Okay, so moving on to the next, the obvious follow-up is horizontal shrinking and stretching. Now, as you would have kind of thought, it's similar because now we are stretching or shrinking the input, right? So the transformation is going to be f of x to f of c times x. And here again, it's going to be a little counterintuitive that when c is more than 1, then you shrink. And if c is between 0 and 1, then you stretch. And the idea is going to be similar to what we saw last time, is that when c is more than 1, things are happening faster, right? That's why it shrinks. And when c is less than 1, things are happening slower, and so it stretches. Okay, so for example, if you're given that this is the function f of x, and you're asked to plot f of 2x and f of 1/2 x, then f of 2x is actually going to be 2 times as fast, right? 2 times as fast means it's going to complete 2 of these cycles for 1 blue cycle. Whereas f of half x, that's going to be, let's use a different color. F of half x is going to be half as slow. So it's actually only going to have 1 cycle for 2 cycles of blue. Okay, so that's how these transformations for horizontal shrinking and stretching works. Let's see, while we are at this, let me just wrap this section up by talking about the reflection property, right? Remember, for example, that in x squared, if I change x squared to negative x whole squared, it gives me back x squared. What that means is there is a symmetry about the y-axis, right? which implies that if I reflect around the y-axis, I don't get anything new. I get the same graph. So we give special names to these functions. We call some functions even function if f of x equals f of negative x, okay, which means they are symmetric about y-axis. For example, x squared, right? X squared is even. And then in the same fashion, we can define an odd function, which is if you take the function and you make the input negative, then the output is also negative. Okay, so for example, x cubed. And if I take negative x cubed, then that is negative x cubed. So you have to add a negative in front to cancel out the effect of that negative. Now for these functions, we say these are symmetric about the origin. For example, if you plot this x cubed function, the x cubed function looks like that. This means if you rotate this 180 degrees, then they remain the same. 180-degree rotation about the origin. Okay, and that's because reflections can be thought of as 180-degree rotations, right? But they're not exactly the same because there's also a mirroring element that happens in reflection, which is not captured by rotation. Okay, example, which of these are odd or even? X to the 5 plus x, 1 minus x to the 4, and 2x minus x squared. Okay, so the best way to do that is, well, let's say these are f of x, f of x, f of x. Okay, so you write down f of x, then you write down f of negative x. So that's going to be negative x to the 5 plus negative x. But negative x to the 5 is negative x to the 5 minus x, which if you factor out a negative 1 is x to the 5 plus x. So this is negative of f of x. Right? So if f of negative x comes out to negative f of x, this means f is odd. What this says is if you make the input negative, then the output also becomes negative. The second one, 1 minus x to the 4, if I make the input negative, this becomes negative x to the 4, or 1 minus x to the 4, which is the same as the function. So this says that making the input negative doesn't change the output, so f is even. Fx is 2x minus x squared. Making the input negative makes it negative 2x minus x squared. But now here, this is not equal to the function, and it's also not equal to the negative of the function, which is alright because this is a special case where it is neither odd nor even. Okay, so because it does not satisfy either of these conditions, we cannot say that these are even or odd in particular for sure. Okay, so this brings us to the end of function transformation ideas. The next thing we are going to learn is going to be composition of function, which is combining functions in a special way. Okay, that's it. Thank you.